Hey guys, so here we are going to start on RL circuits. They are almost exactly the same. Right? They behave slightly different than capacitor, but the concept is exactly the same. So I'm going to walk you through the similar steps that we did for RC. So let's begin. All right. So I want to look at the relationship. That's how we began RC. I want to look at the relationship between the voltage and current again in inductor. Let's see what that looks like. Remember, guys, how capacitors voltage lagged 90 degrees behind the current? Well, what's happening to our excuse me, our inductors, right? What's happening to our inductors? Well, same idea. I'm going to use the red for current, and this time I'll use, I don't know, I'll just use the yellow. It's fine. All right, so what's happening? What's happening in the inductor when you first close the circuit? What's coming first? Is it the current or is it the force? Do you guys remember the Lenz's law, right? It is going to, whatever the EMF or current that has been generated by the magnetic flux, it's going to oppose in the direction that it came, right? That made it, right? So that's exactly what's going to happen. For inductor, if you close the switch, current is wanting to flow, but it is blocked by the force that is generated by these coils in the inductor. It's pushing back. It's like the teenagers. It's like the teenagers that I explained before. It's very difficult. It always wants the exact opposite. When you tell them to get up in the morning, they will do everything to stay in bed. And at nighttime, if you tell them to go to bed, well, they will do everything in their ability to stay up as long as they can. So that's it's a force, right? So the force we have right there, this is going to be I grab the current pen. So let's redraw this. I apologize. Okay, so this is the voltage for inductor and maximum amount of voltage and resist, and eventually they're going to give in. They're going to get up and go to school, or they're going to go to bed. Eventually they're so tired. That's my VL. What about my current? What about my current? Because at first it's not flowing because my voltage was pushing back with the exact same amount of force, but slowly it's letting it off. Now the current is flowing. Right? This is my current. It's exact opposite as capacitor. Capacitor, current always started, but voltage. For inductor, the voltage starts first. Okay, let's see what happens here. Same thing again, guys. I'm going to label this. So that's 90, that's 180, 270, and 360. Okay, and that's 0, obviously. Okay, so always referencing the resistor, that doesn't change. Resistor, I used orange, and I'm going to do this. Okay, and that is going on. What about my current? What about my current? Current travels exactly the same as the voltage, right? The resistor voltage. Oh, I forgot to label that. I, right? And my VR, right? Orange for VR and red for I. Okay, now, what about my voltage for inductor? What about my voltage for inductor? Well, let's look at it. When the current is 0, where was my voltage for inductor? It's at maximum. what about when the current was at maximum? Oh, my voltage was 0. Do you guys see that? And again, when my current is back to 0, because it's the other cycle, and voltage is back to maximum again. And when the current is maximum, the voltage for inductor is 0 again, and that repeats. So you're going to end up with this graph of VL. Isn't that funny? The capacitor started here, it lagged, but it looks like this guy is ahead. The voltage for the inductor is ahead of the VR and I. So let's take the VR again, just like we did for capacitor, and let's focus on the I. And I want to focus on VL. I want to position that guy as my reference. All right? Again, this is 180. 90, 270, 360, 0. Okay, so that's my VL. Where's my current? My current is, when it's at maximum, it's finally starting. Oh, taste of its own medicine, isn't it? There. When the voltage for the inductor was minimum or 0, current was maximum, vice versa. When the voltage for the inductor was maximum, current was 0 again, so on and so forth. And which didn't start. So you can see this relationship. It's now 90 degrees ahead. 90 degrees ahead. My voltage for the inductor is 90 degrees ahead of the VR and I. So how is that going to look like in our diagram? Well, let's draw one right here, my phasor diagram, because I already introduced what the phasor diagram is. It's my 0, 90, 180, and 270. This was VR, right? That doesn't change. Resistor family, the main unit, right? But these guys pay the premium. The inductor guys, they're a little bit more fussy, so they want to live upstairs. They don't mind paying a bit more money. All right, upstairs guys, so they're 90 degrees ahead, because when it's 0 degrees, when the current is 0 degrees and the voltage, where was the other guy? 90 degrees ahead, 90 degrees ahead he started. Right? So this is where our VL family, sorry, the inductor family lives. I don't even know why I'm writing L here. Right. XL and XL. Okay, makes sense? Right? So it's flipped 180 degrees. Capacitor lived right there, but then now the inductor lives 90 degrees up. They're ahead of this guy. Right? That's the only difference, guys. What do you think the calculation is going to be? Same idea? Yes, it is, except the inductance, reactance is going to be slightly different formula, but everything else is exactly the same. So let's get to it. All right, so same idea from before. I've moved the graphs onto the left-hand side, and here is my RL circuit in AC. So I said the idea is exactly the same. Now I have to tell you what the XL formula is, and that is represented as XL is equal to 2 pi FL. Oh, we got rid of the reciprocal. 1 over. So much easier to calculate. What does that mean? Like I said, my inductors, and the 2 pi is a constant value, and so I can vary the frequency, which means it has a direct relationship. If this goes up, that goes up. If the frequency goes down, then the reactance of the inductor goes down as well. It's a direct relationship. We have the Air Cadets performance going on at nighttime usually. And I hope it doesn't bleed, the sound doesn't bleed through my mic here. They're like blowing trumpets and horns and stuff like that. Anyways, yeah, hope it doesn't affect my mic. So first step, we're gonna find XL, right? Because we need to find a total impedance, right? A total impedance we have to find. And from that, we can find the total current, then we can find everything else, right? So what is my total reactance? Total reactance is 2 pi FL, meaning 2 pi times 3K and times it by millihenry. I like inductors too because it's such an easy number to input instead of like the capacitor that has like a nano and pico and stuff like that. Oh, goodness me. Anyways, let's put that in the calculator and see what you get, and you should be getting that. All right, that is the value of the reactance for inductor. Okay, how about my Z, my total impedance? Total impedance will go exactly the same, guys. Instead, if we were to look at the phasor diagram, anyone live down there? There is a capacitor. Nope, no one. So we can erase this guy, right? All right. So, I'm forgetting the colors that I was using. Anyways, always label them first. VR is 2500, which is right there, 2500 ohms. And not the VR, the resistant. I'm sorry, I'm doing that. It's late at night right now. Anyways, capacitor, inductor reactance is 2262. It's slightly less than this, about the same. I would say like right there. Okay, 2262 ohms, and I'm gonna label that XL and VL. Sounds fair? Perfect. Look at that. How do we calculate RZ? Oh, it's vectors again. Does that move? No, it doesn't move. It stays where it is. And we're going to be moving start to finish. So this must begin where it finishes, right? From here to there. Let me draw that like that. And that's going to give you that value. Boom, right there. That is your impedance. Does that look familiar? Yes, it is a Pythagoras theorem. So we can say that RZ is square root of R squared plus XL squared. We just replaced XC with XL, right? Pretty straightforward. Like I said, I told you this is super easy. Okay, let's do that again. R is 2500 square plus 2262. And that is going to give you a value of 3371 ohms. Oh, the air cadets are playing a whole new world from Aladdin. It's kind of a nice tune to listen to. I hope you guys are not listening though to that. I can't listen to it. Anyways, 3371 is my total impedance value. Lovely. Okay. What else can we calculate from there? We have the total impedance. I can calculate the total current. What is my total current? It is the 18 volts divided by the total impedance, and that is going to give you, what is that? I don't have that answer prepared. 18 divided by 3371 is 0.00534. Otherwise, it means it's 5.34 milliamps. Good. Let's calculate the rest of them. VL, VC, VR, that's what I meant to say. VR, okay, times VL XL 2262. That will be IT times XL 2.8 volts. Perfect. I hope you guys are getting the same thing here. We're doing this live. Perfect. What else? Since we got all of these values, what else can we do? How about a theta? Remember that? The theta lies with, again, a reference to our voltage for resistance or resistance, right? It's never up here. It always wants to side with our reference line, all right? Just like our capacitor, I see how it lied next to our reference line. Same idea, guys. And since we haven't used the tangent, let's use tangent. Tan inverse of that is, it's opposite over adjacent. Opposite, which is 2262 over adjacent, which is 2500. Adjacent, next to it, this is hypotenuse. And that is going to give you 42.13 degrees. 42.13 degrees. Yep, guys getting that? Perfect. Can we calculate now power factor? Can we do a power factor now? Absolutely can. What do you guys want to use? You guys want to use the voltage, or you guys want to use the resistance value? Well, I've put in more effort calculating voltage. I'm going to use the voltage. So how do you calculate power factor using a voltage? Remember, it's the same triangle. So VR, which is going to be 13.35 over the total. Right, oh, sorry, not the total. This is not total. This is total. What was my total? 18. I'll just write that down there for you guys. VS. And that is going to give you a number of 0.74. Converted into percentage is 74%. 74% effective circuit is a little bit better than a capacitor circuit, but it's just for this circuit only, guys. It really depends on the frequency, right? If I increase the frequency now, I'm pulling up this whole thing. I'm pulling it up. Lower the frequency, I'm pulling this down to where the R is. But higher the frequency, higher the value of the reactance for inductor. Okay, see that relationship? That's what it is. If I went up to, let's say, 5,000, 6,000, this is going to be half the efficiency of that. It'll be like 30-something% effective, which is not good. How did that work, guys? Was that good? Right? Always prepare to do this math, which is really a Ohm's law, VIR, with extra optional accessory that was added to it, right? And some Pythagoras theorem to calculate your angle and power factor, but that's it. You guys should know how to draw the phasor diagram as well. We're going to be using this phasor diagram a lot. In the next lecture, we will talk about resistor, capacitor, and inductor all together. What happens if we put all three components together in a circuit? Sounds interesting, right? That's going to be our next lecture. I will throw another quiz for you guys on this RL. I want you guys to solve it yourself, right? And compare the answers with me at the end. But yeah, that's it.